At this point, we're going to take a little detour from our macroscopic description of entropy, where we've talked about how it's, what drives spontaneous processes, to understanding what's happening on a molecular level. What's the molecular basis of entropy? And this ends up involving statistics. And so first, I'll introduce the equation that describes this. Entropy is equal to the Boltzmann constant times the natural log of W, and we'll get into what W means in just a little bit. And this equation was postulated by Ludwig Boltzmann of the Boltzmann constant, and that constant there is the Boltzmann constant that's named after him. And this is a way for us to understand. We have made statements like, you've probably seen statements like this in other classes, that entropy is a measure of the disorder of the system. And that's not very quantitative. It doesn't really help us to have a fundamental understanding of what's happening here. And so we need an actual quantitative basis to understand entropy, thinking of what's happening with molecules on the molecular level. And that's where this equation comes in. Now, the key variable in this equation is this W term. And W is a term that we call the multiplicity of a state. Now, what does that mean? The multiplicity is the number of equivalent microstates. Now, we're going to introduce some more terms that we're going to have to define. But the number of equivalent microstates that correspond to a given macrostate. Okay, what does that mean? The best way to explain this is by example, an example where we're looking at a small number of particles. So let's imagine we have a quantum system that can be in 4 different energy levels. Energy levels 0, 1, 2, and 3. And each of these has an energy equal to that level, right? So we're not giving any specific units here, but if a molecule is in the 0 state, it has energy equals 0. This has E equal to 1, E equal to 2, E equal to 3. Just to keep things simple, and there's only these 4 possible states. Now let's imagine we have 3 molecules, and there are 3 units of energy to disperse amongst these 3 molecules. Okay, now there are a few different ways that the molecules could be arranged. All right, so let's imagine we have 3 molecules in state 1. So if we sort of depict this pictorially, we can draw sort of 3 circles here to represent there's 3 molecules in state 1. Now, how many ways are there to do? So this would be our macro state. So now there are different possible microstates that we could, actually in this case, there's only one possible microstate. So if we labeled each of these molecules 1, 2, and 3, they all have to be in state 1 for this to work. And so we would say that for this particular macrostate, W equals 1. Okay. Another possibility is we could have one molecule in state 3 and the other 2 in state 0. All right. And now we sort of have to keep track of the molecules. Actually, let me label these now A, B, and C. That way we have fewer numbers we're dealing with. All right, so if we consider A, B, and C molecules, we could have A be our molecule in state 3 and B and C be the ones in the lowest state. We could have A and C in the ground state and B in the excited state. Or we could have A and B in the ground state and C be the one up in state 3. Right, so now there are 3 possible ways to do this. So we would say that W equals 3. And this isn't the only possibility. We can also have one molecule in 2 and one molecule in state 1. right? And we could write out all these possibilities, but this would work out to be 6 different ways. Okay, so what we're getting at here is that if we just sort of if we pick one of these at random, we have a total of 6 plus 3 plus 1, 10 possible ways. 10 possible ways these 3 molecules could have 3 units of energy sort of dispersed among these states. But by far, the most probable one is this one right here, because there are 6 different ways to do it. We have a 6 out of 10 chance that our molecules will be arranged this way, just based on random chance, right? We have a 3 in 10 chance that they're here, and we have a 1 in 10 chance that they all are in the same state. They're organized, and so that's something you may notice, right? Is that our most probable state over here on the right, we have our molecules spread out to different energy levels. And that is what, and that's what we're getting at here. Okay, so we need to define how we mathematically determine W, and we'll get to that in the next video.